Thank you for joining us on another online VCR VHS adventure on YouTube. Today I really like the presenter in this one. I hope you'll enjoy it as well. Some of the music is also super duper top notch.
Hi, I'm David I work for Borland International. My job is to talk to people about programming. In this video, I'll be helping you learn about C++. For C programmers, C++ is the modern way to program. And it's going to make your life, or at least your life as a programmer, a lot easier. As programmers, the part of our job we like least is maintenance. We all love to write new programs, to solve new problems. Unfortunately, most of us spend more than half our time maintaining old programs. C++ is changing all that because it's an object-oriented programming language. Unless you've been marooned on an Aleutian island for the past few years, you've probably heard of object-oriented programming, which some people call OOP. OOP is a way of programming that gives you a lot of advantages, like reusing existing code without changing it, or even completely understanding it. Why should you take perfectly good code and completely rewrite it, when all you want to do is add a few features? With C++, you can add features on top of existing code. That way, if something doesn't work right, the amount of code you have to debug is quite a bit smaller. And that's only the beginning of the benefits you'll get by programming in C++. Listen to Bjarne Strustrup, the creator of C++.
The key difference is that you try to work at a higher conceptual level. When people start writing a program in C, they get to the bits and bytes very fast. With a language like C++ and object-oriented programming in general, start by saying more in the lines of, now what are the fundamental concepts in my application? How do they relate to each other? Can we express the relationships between those fundamental concepts directly? In other words, the design phase that some people have tried to sort of superimpose over a traditional programming language, and not always with very much success, becomes a natural part of programming because you can separate the process into design your concept, find their relationships. Now, when you've got a good framework, write your program. You can write programs faster. You get higher quality code. It gets easier to understand and easier to maintain, and you can build better tools for it. That just follows from raising the level of abstraction. That's what we're trying to do.
You'll learn that every new feature in C++ supports the creation of new data types. After all, that's the primary activity in C++. In the next lesson, we'll look at more features of object-oriented programming and the way we classify objects into types, just like we would in, well, the real world. When you view an object in the world, often the first thing you consider is what type object it is. Organizing the world into types is such an automatic process, we are often not even aware of it. The type of an object helps us keep track of the characteristics and behaviors of objects in the real world. By classifying objects into hierarchies of types, we are able to determine information about the object's characteristics and behavior that would otherwise require a lot of work to discover. When a new type of object is introduced, we can assume things about the object because we have an understanding of how it relates to other types in the hierarchy. The reason programming is difficult and expensive is the way we model a problem in the computer. It doesn't coincide with the way we perceive the world in our own minds. In fact, the way we model our problems tends to look like a computer. And then, this is what happens. Utz was right. Software does change. No matter how well thought out a problem is, somebody will come up with a better idea once you've got the program running. These changes to add new features cause the design and documentation to be compromised, which is why we need C++. When we create libraries, we try to reuse the work that we and other people have done. Unfortunately, using C libraries is especially difficult if they don't do exactly what you want. The minute you have to change the source code, if you can get it, you could add bugs to a previously working piece of code. Wouldn't it be nice if we could represent and manipulate our system in the computer the same way we view it in the real world? That is, in terms of types? Wouldn't it be nice if we could use most of what we know about a set of types when a new type is added to the picture? And wouldn't it be nice if libraries were much easier to use and more robust, and we could make additions and changes to libraries without corrupting the original code? This is what object-oriented programming is all about. It helps you create larger, more complex programs with fewer programmers and expense. It makes those programs easy to maintain and extend, resulting in libraries which are easy to use and reuse. This allows you to get your job done in a lot less time, leaving more time for other activities. Object-oriented programming allows you to represent a type in the problem space as a type in the computer. Like types we see in the real world, each type in the computer has characteristics and behaviors. Object-oriented programming also allows you to create families or hierarchies of types to duplicate the way we classify objects in the real world. When we want to get information about an object or tell an object to do something, we send a message to that object. Each object does the appropriate action when it receives the message. In the real world, new objects appear every day. Things do change. How will the program be able to handle a new object added to the system? Objects that are similar can share the same attributes and behaviors, even if you don't know at compile time precisely what type of object it is. The message will be handled properly by the object. Once we design a type, we can create many instances, also called objects or variables, of that type. An object-oriented language must support 3 features. Abstract data typing is the creation of new types. We do this in C++ by extending the C struct to allow member functions as well as member data. Once we create a new type, we can have many variables of that type called instances or objects in C++. Inheritance allows us to create specific types from more general types, to create hierarchies of types, and to make changes to existing types without corrupting the original code. Inheritance is one of the important ways C++ supports code reuse. Polymorphism allows you to create a common interface as a set of member functions to a hierarchy of types. Each object handles a message in its own special way. Polymorphism allows us to create generic and extensible programs which are easy to extend. If a new type appears in the problem, we simply add it to the existing hierarchy, and define its particular behaviors. Extensibility means adding features to a program is easy and inexpensive. Object-oriented languages support an additional important feature, dynamic object creation. This allows you to establish the number, type, and lifetime of objects at runtime. In some situations, you know this information while you write the program, but in most cases, you don't. The classic bank teller problem is a good example of an application that requires dynamic object creation. You never know how many customers are going to arrive at any time, or how many tellers you have to have available, and this affects how long you have to wait in line. Throughout this video, we'll examine the way C++ implements the features of an object-oriented programming language, and what makes it a better C. In Lesson 2, we'll look at the way you create new types in C++ by adding functions to structs. In Lesson 1, we saw how the concept of a type is fundamental to object-oriented programming and to building an image in the computer of the problem we want to solve. In this lesson, we'll see how C++ implements new types. Suppose you want to build a system consisting of several elevators. In C, you typically attack the problem by creating a struct to hold data about each elevator. Here's how you might solve the problem in C. First, a structure is created which holds all the information we want to remember about each elevator. To create a variable, you use the struct keyword along with the structure name. As this might be unwieldy, you can use a typedef in C to make a struct act a bit more like a built-in type. When you create a function to act upon the struct, you must pass as an argument to the function a pointer to the struct. For example, you can make a function to initialize the fields, and another to select the floor. You can see that everywhere we want to use the elevator, we must dereference a pointer. We must use pointers rather than passing the elevator struct by value because we are modifying variables outside the scope of the function. Passing by value would simply make a local copy. Now let's see how we might solve the same problem in C++. In Lesson 1, we described a type as having characteristics and behaviors. C++ implements a type as an extended struct, a struct which contains function declarations as well as data declarations. Collectively, these are called members. Data members represent the state of the variable, and function members are the operations which can be performed on the variable. Let's see what this looks like in code. First, notice that C++ has an additional comment syntax. The double / starts a comment at any point in a line. The comment continues to the end of the current line. Existing C code must also be compiled, however, so the old comment syntax still works. Next, notice that in the C version of the elevator program, we did not include the header file containing the declaration of printf. Although it's always a good idea to declare functions before using them, it is not required in ANSI C. In C++, however, all functions must be declared with full prototypes. That is, all the argument types must also be declared before the function can be called. Now here's where C++ is very different from C. Notice that functions are declared inside a struct. The scope of these member functions is the scope of the struct. These are not global names. When defining member functions, you must tell the compiler that the function is associated with a particular type using the scope resolution operator, the double colon. Since the member function is in the scope of a struct, it has access to the other members of the struct. No pointers are necessary. Defining a variable of a user-defined type is just like defining a variable of a built-in type. However, we did not have to create a typedef as we did in C. When calling a member function, you must specify an object. Calling a member function, or sending a message to an object, is just like selecting a data member of a struct. Since the user doesn't have to pass the address of the variable into a function, member function calls are easier and cleaner to use. In the next lesson, we'll look at how C++ provides data hiding mechanisms to prevent undesirable access to members of an object. In the last lesson, we talked about how a type is represented in C++ by extending a struct to include functions as well as data. But if a programmer still has direct access to all the members in a struct, the data is unprotected, and programmers can get into it and mess things up. So we need to protect the data. Why? Well, first of all, sometimes modifying one data element may require modification of another to maintain the integrity of the object. If you can deny programmers access to certain data elements, that forces them to use member functions, which you can design to preserve object integrity. Or, in a struct where all members may be modified, it can be difficult for programmers to know which interface they are supposed to use. By denying access to some of the members within a struct, they can only use members that are part of the public interface. Then you don't have to yell at them for screwing up your system. A third reason why data protection is so important is that it helps you isolate bugs. Say a programmer makes an incorrect modification to a member and suddenly you have an error somewhere in your system. If all of the members are public, that error could be coming from anywhere. But if some of those members are private, you know the problem must be coming from functions which have permission to access data. I told you C++ would make your life easier. So how does C++ address these security issues? C++ adds 3 new keywords to provide data protection. These are called access specifiers and include a colon. Public means that members declared after this point are accessible by everyone. Public members are like members of C structs. C++ structs default to public access. Private means that all members declared after this point are only accessible to other members of the object. Other programmers cannot access private members, so they are safe from accidental changes and are not part of the public interface to the type. Protected members, like private members, are not accessible by other programmers and can only be modified by other members of the type. However, member functions in derived types, a subject we'll cover in Lesson 14, can access protected members of the base type. Let's see how we can use access specifiers to increase the integrity of the elevator type in Lesson 2. The only way to modify the private data elements is through the public interface. For example, we cannot do this. The compiler will generate an error. You can use access specifiers as many times as you want within a struct. Although this is syntactically correct, it isn't recommended because it reduces readability. Member functions can also have restricted access like this. Here, we can assume that move calls translate, since programmers using the object cannot. In this lesson, we've learned why we need to protect the data and functions within types, and how the keywords public and private can help us do that. In Lesson 4, we'll talk about another new keyword, class.
Strictly for the structs, it's time for class. You're going to get protection and you're going to have to pass. It's an abstract experience as you will see. And if you pass for class, then you can chill with me. Now you can make it a new type, believe that it's no hype. But some of you might not like it, then go take a hike. It's back to C, and you will see, yeah.
In the last lesson, we talked about data protection and how C++ controls access to structural elements. In this lesson, you'll learn about another way to protect your work, classes. Now, a class is exactly the same thing as a struct, with one key difference. Structs default to public, so all the data within them is available to programmers. On the other hand, classes default to private, so using classes is another way of hiding data within C++. Classes are an important concept within C++. So important, in fact, that when Bjarne Strostrup created the language, he called it C with classes. It wasn't called C++ for another 3 years. But who cares about history? You need to know how it works. Now, all examples we've used so far, which begin with this, can be replaced with this to achieve exactly the same effect. In general, you should use class instead of struct when you're creating new types. Struct is appropriate when creating C-style data structures, or when you want to emphasize that all members are public. In C++, 4 keywords behave in a similar fashion. The declaration form of each is similar, and the name used with each becomes a reserved word within its scope. In effect, a new type name, although union and enum lack most of the important characteristics of a type. In C, you must use the keywords struct, union, and enum when defining variables. But in C++, the equivalent of a type def is performed for you. Here are the 4 forms of declaration and definition comparing the C to the C++ forms. A class, a struct, a union, and an enumeration. For backward compatibility with C, the C forms are still accepted by C++, but the C++ syntax tends to be more comfortable and easy to remember. That's it for this lesson about classes. Just remember that a class is exactly like a struct, except that a struct defaults to public and a class defaults to private. We also learned 2 other keywords for declaration and definition, union and enum. In Lesson 5, I'll show you how C++ lets you use the same function name in different ways. The time has come to speak of function overloading and default arguments. Now, the neat thing about these 2 features of C++ is that they let you use the same function name in a lot of different situations, which makes sense. The concept of print, or hide, or show, or whatever is the same, even though the name of the data changes. Say I want to send this letter and these packages. Letters I send using the US mail. This package is a tape of my twins cleaning their room. I'm sending it to Grandma via UPS. This third package is some software I need to send to a colleague. It absolutely positively has to get there overnight, so I'm sending it Federal Express. Suppose you want to create a print function, and you want to give it various types of arguments: char, char pointer, int, and double. In C, you might come up with something like this. Although it's the same concept, printing, you must create a different name for each implementation of the concept. Not only must you create these names, you must explain them to the user of your library. Now, suppose the user has mastered this group of print functions and then decides to use another library which has a way to print an elevator. If the function declarations are all made in the same file, the C compiler will give an error message about a type mismatch in the redeclaration of print. If the colliding declarations are not made in the same file, the C compiler won't catch the error. The linker will detect a multiple definition error. If there's only one definition, but 2 different declarations in 2 different files, neither the compiler nor the linker will catch it. We'll look at this type of problem in the next lesson. To solve the problem of name collisions between libraries in C, library authors must not only create function names to differentiate the type of arguments, but also to differentiate one library from another. C++ provides function overloading. You can use the same function name for many different functions, as long as all the functions have distinct argument lists. In this case, we can create the following functions. The concept of printing is the same for all the functions, but its use is different. All the functions have different argument lists. Overloaded functions must have different argument lists, even if the difference is just in the ordering of the lists, like this. Overloaded functions can have any return value, but two overloaded functions cannot differ by only the return value. For example, you cannot do this. The only time two function declarations will clash is if they have identical argument lists, which is a logically ambiguous situation. C++ has a second feature to allow more flexible use of function names. It's called default arguments, and this is what it looks like. Now you can call the function send in 3 different ways. Here, the compiler will automatically substitute test and 1 for the first and second arguments. Here, the compiler uses hello as the first argument and substitutes 1 for the second argument. And finally, here the compiler uses both arguments provided in the call and doesn't do any substitution. Default arguments look a lot like function overloading, since you can use the same name and different arguments when you call the function. However, there is no overloading when default arguments are used. The compiler is performing the argument substitution and calling the same function. You can use overloading and default arguments together as long as no ambiguities are created. There are some restrictions when using default arguments. Only trailing arguments can be defaulted. And once you start, all the rest of the arguments in the list must have defaults. Thus, these are illegal. You can only use default arguments in the function declaration, and the default arguments can only be declared once, although the function can be declared more than once. The default arguments may not be redeclared in the function definition. This redeclaration of the default arguments is illegal, and this specification of default arguments in the definition is illegal. In this lesson, we've learned how function overloading and default arguments work. And we've seen how they make programming easier by letting you use the same function name in different libraries. But there are even more highlights ahead, and in Lesson 6, those highlights will be about type-safe linkage. In Lesson 5, we saw how function overloading can eliminate a problem arising when two different libraries use the same function name. In this lesson, we'll see how C++ can prevent a more insidious problem which occurs in larger projects with multiple files. C++ requires all functions to be declared with full prototypes before they are used. This eliminates a large class of problems. However, there's still an error which occurs when the prototype is incorrect. Presumably, this happens when it's written directly by the programmer rather than being contained in an include file. For example, if the prototype is incorrect, you'll have a problem which can only be detected by recognizing the error in the prototype. Since you've prototyped the function, you may be assuming there cannot be a problem, so you will not be looking for it. This can be a real mystery, especially in a large project or when working in teams. The C++ compiler by itself cannot detect this type of error either. In effect, the incorrect prototype is deliberately misleading the compiler, so it goes along with what you've told it and compiles the file without complaint. Remember that in the workbook section for Lesson 5, we discovered that all function names are encoded, or mangled, by the compiler to allow function overloading. The function names may be the same, but the encoded names are distinct because their argument types have been included in the generated name. This solves our problem. In C++, this is called type-safe linkage, because the linker now has information to ensure type safety in function calls. Here's how it works. If this program is compiled with C++, the compiler will generate this name for the function call. The function name now contains the fact that it expects an integer argument. Now let's look at the print function compiled with C++. The name generated for the function is different. The argument type has been encoded into the name. Now, in effect, the linker has information about both the function name and its argument types. When the linker is trying to resolve the call, it will be unable to find the function and will report an error. Type-safe linkage means dangerous errors of incorrect typing will be caught. C++ allows you to call C functions, even those C functions which have not been compiled with the C++ compiler. This presents a problem. If a function call generates a mangled name, and the C compiler doesn't mangle names, the linker won't be able to resolve the function call. How can we call C functions from within C++ code? There is a special mechanism within C++ that allows this, called an alternate linkage specification. It tells the compiler to change the encoding of function names. Here's what it looks like. Now we can successfully compile and link with the C version of the print function. Type-safe linkage is a safety feature in C++. It won't show up unless you make a mistake. However, it eliminates an important type of error. In the next lesson, we'll look at how C++ allows you to automatically initialize and clean up variables of user-defined types. Oh, hi! In this lesson, we're going to talk about constructors and destructors. You see, the concept of creating new data types, or designing new data types, is the foundation of C++. What constructors do is make sure objects are properly initialized. Now with C, you're probably used to doing that initialization yourself. What that means, though, is that you have to remember to actually do the initializing. When we introduced types in lessons 2 through 4, we used an example of an elevator. The initialize function sets the initial values of the floor selected and the current floor number. In C, when you define a variable of a built-in type, you expect the initial value to be garbage, so you must always initialize it before you use it. However, if you forget to initialize an int, for instance, the garbage value it contains will still be a legitimate int value, and similarly for the other built-in types. If we do not call the initialize function for elevator, however, the initial state of the elevator will probably not be legitimate. Floor number 1001 or floor selected minus 47. Forgetting initialization is even more critical if the class contains pointers. When creating user-defined types, then, it is essential to be able to ensure proper initialization. C++ has a feature to guarantee proper initialization, the constructor. The constructor is a special member function which has the same name as the class. If we changed the initialize function to a constructor, it will look like this. Notice that a constructor has no return value. This is different from a void return value. Defining a constructor follows the same rules as other member functions. The constructor is called automatically when you define a variable. Initialization now happens at the point of definition of the variable before the programmer can even access the variable. Since the constructor is called automatically, we can guarantee proper initialization of variables. This eliminates a large source of errors. Constructors are often overloaded. The constructor with no arguments that we've defined here is called the default constructor. It's called by the compiler when no arguments are available. Constructors can have arguments. Here's an overloaded constructor. Calling a constructor with arguments is simply a matter of adding an argument list after the variable name. We can also use default arguments in the constructor. However, we couldn't make both of the arguments default because this would cause an ambiguity between the two constructors. The compiler wouldn't know which one to use with no arguments and would generate an error message. Constructors also automatically perform certain other initializations, which we will see in future lessons. Proper initialization of objects is important. Constructors do that. But we need destructors too, because once we finish with an object, we might need to do some cleanup. If we continue with our elevator example, cleanup might involve bringing all the elevators back to floor 0 when you shut down the elevator system. That's what a destructor can do. A destructor is the class name with a tilde in front of it. Here's how it looks on the screen. You can only have one destructor, and it cannot have any arguments. The definition for the destructor is just like the other member functions. Like the constructor, the destructor calls are not made by you, but by the compiler. Without any further changes to the program, the destructor will be called at the point where the two variables go out of scope. This will cause both elevators to move to the ground floor when the program shuts down. With constructors and destructors, we can create objects with proper initialization and destroy them with proper cleanup. That means you can avoid a whole class of errors. C programmers commonly use the preprocessor to make code easier to write and read with value substitution and macros. In this lesson, we'll see how this process invites errors because value substitution looks like an expression but doesn't act like one, and because a macro looks like a function but doesn't act like one. Then we'll see how C++ rectifies the problem with consts and inline functions. Value substitution is useful because it allows us to take a name and substitute it everywhere we would normally place a value, like this. This is a good programming practice. The program is easier to understand, and you can easily change size. A problem occurs in value substitution because the preprocessor does textual substitution and doesn't follow the normal rules of the compiler. Thus, an expression may look like a normal C expression, but it may not act like it. This can cause errors which are difficult to find. Suppose we make an innocent modification to the above program. All we've done is multiply size by 2, but the results are unexpected. If size were a C variable, this wouldn't happen, since the operator precedence would occur as you would expect. You may observe that this problem can be avoided by the proper use of parentheses. But if code like this gets buried and you aren't looking for it, it can be very difficult to find. You might think you could solve the problem by making size a const, but ANSI C treats a const differently than a preprocessor name. A C const is a variable that cannot be changed. The name of the const is global. This is also called external linkage. You cannot place a const definition in a header file because it would then be defined in more than one place. A const in C always allocates storage, so you don't save any space. The C compiler cannot evaluate a constant expression which contains a const. So if size is a const, you can't say this in ANSI C. Therefore, in C, const cannot replace the use of the preprocessor. In C++, const has a distinctly different meaning than in ANSI C. A C++ const defaults to internal linkage, which means it is static and can be included in header files where you would normally place a hash define. If possible, the compiler will not allocate space for a const. Instead, it will evaluate the expression and store the result in its symbol table. Then it can use that result after performing type checking in a constant expression. Thus, in C++, we can use a const just like a preprocessor value, like this. The constant expression is evaluated at compile time, so it can be used in the array definition. Therefore, in C++, const has all the benefits of using the preprocessor, plus you get the safety of type checking. There is no situation where it is better to use hash define for variable substitution. You always get much better benefits from using const. The second important place where the preprocessor is used is for code substitution with macros. The problem here is that a preprocessor macro looks like a function, but doesn't act like one. Here is a macro and a function containing exactly the same code. They call error if the argument is out of range. If we make the following rather innocent calls, we get a number of unexpected results. We get different results depending on whether the function or macro is called, and also depending on the value of the argument. The problem occurs because the macros are expanded like this. The execution of the first macro decrements x for both tests and the call to error. The execution of the second macro only increments x for the first test, which evaluates to true, so the second test is short-circuited. But it also increments x for the call to error. In C, the only way to write small function-like entities which have no function call overhead is to use the preprocessor. In C++, preprocessor macros were considered problematic enough to add a new feature to the language. Inline is a C++ keyword which tells the compiler to treat a function as a macro. When the C++ compiler encounters an inline function, it doesn't allocate storage for the function body as it would with a normal function. Instead, the compiler creates space in its symbol table and stores the prototype of the function and the function body in the symbol table. Thus, the function definition generates no object code at the point it is defined. When you call an inline function, assuming everything is correct, the compiler inserts the function code directly in line, giving you the efficiency of a macro. Everything else about an inline function is exactly the same as a normal function. You get type checking on the arguments and return values, and there are no surprise, non-function-like interactions. Thus, there is no confusion about the behavior of an inline function, since it is exactly the same as a regular function. The only difference between an inline function and a non-inline function is the use of the inline keyword. Because an inline function doesn't generate any code at the point it's defined, you can put inline definitions in header files just like macros. In fact, there's almost no place a preprocessor macro is used that an inline isn't better. Although global functions must be explicitly declared inline, any function which is defined within a class declaration is automatically inline. Here's an inline constructor. In the next lesson, we'll see the flexible way that C++ allows us to define variables and what the word object means. Okay, defining objects. In this lesson, we're going to talk about defining variables and how C++ makes that easier. But first, let's cover a few definitions. A declaration tells the compiler that a name exists someplace, and it gives type information about that name. You can declare data, functions, and classes like this. When you are declaring data, you must use the keyword extern. However, extern is optional when declaring functions, since the compiler can see there is no function body, so it must be a declaration. Note that a C++ function declaration with an empty argument list means no arguments, unlike ANSI C where it means any number or type of arguments. The declaration of window is called a class name declaration. It merely tells the compiler that the name is a class, but nothing else. The declaration for door is called a class declaration, since it contains a body, but doesn't cause any storage to be allocated. A definition causes storage to be allocated for a name. This storage may be on the stack, in the global and static data area, in the constant data area, or in the executable code area. We normally think of an object as something we can send messages to, that is, a variable of a class. However, in the most general sense, an object is a region of storage. Thus, the term variable and object are often used interchangeably. We learned previously that uninitialized objects are bad. That's one of the basic philosophies of C++. To make sure everything is properly initialized, C++ includes constructors and destructors. Remember them? Unfortunately, a constructor with arguments may need information that you don't have until some code has been executed. So what do? Well, if you were programming in C, you'd be up some unnamed creek because you have to define all variables at the beginning of a block. This is a problem for two reasons. The first is that the name X is in scope and can be used before it's been initialized. The second problem occurs if X is a class object with a constructor. What if you cannot create X without an initialization value? If X class does not have a default constructor, you must expect to be able to define X further down in the code like this. This is exactly what C++ allows. You can define a variable at any point in a scope. The variable is only available from the point of its definition until the end of the scope. This means you can wait until the point in the code where you need a variable and you have all the necessary information to initialize the variable before defining it. To look at variable initialization, we'll create a class with a constructor and a destructor which announce themselves. Ident in this class is simply a single character, which we hand the constructor so the object has a recognizable name. Now let's use this class to track variable initialization. Notice how the definition of B occurs after the code for putS has been executed. This is not allowed in C, only in C++. A common place to define a variable, although it may be surprising at first, is inside the expression of a for loop. Here it is obvious to the reader what I is for. You wouldn't know it is a loop counter by seeing it at the beginning of a block. Notice that all the variables, even built-in types, are initialized at the point they are defined. Because you can define a variable at any point in a block, you can always initialize variables when you define them. This provides one more level of safety when programming in C++. C++ also allows more sophisticated initialization than C. For instance, you can define and initialize arrays of objects. To demonstrate this, we'll create a slightly modified version of the class which announces construction and destruction. We've added a default constructor, one with no arguments, which is used by the compiler when initializing objects such as temporaries and arrays. For instance, here, the compiler creates space for an array of 3x objects. At runtime, the default constructor is called for each of the objects in the array, which is something you'd have to do with a loop in C. The user cannot even access the elements of the array before the constructor is called. The destructor is also called for each object in the array. You are not forced to use the default constructor. You can call the constructor with arguments by providing a list after the array. You can let the compiler count the number of initializers in your list and use that to determine the array size. The initializers in the list can even be expressions or function calls, as long as they produce the correct value to use as the constructor argument. This is often called aggregate initialization. Because C++ lets you define a variable at any point in a scope, you have a lot more flexibility in programming, not to mention the added convenience, safety, and readability. So that's Lesson 9. We're almost halfway there. I'll meet you back here for Lesson 10, and we'll talk about manipulating object addresses. Okay, time for the next lesson. Now we've been talking about objects a lot, but so far only as places where data and functions are stored. However, objects have to exist someplace, don't we all? So we need to deal with their addresses. Each object has an address. And in this lesson, we'll look at two ways of manipulating object addresses. Pointers, which work like they do in C, and references, a new feature in C++. As you work with C++, you'll probably find that references are a lot easier to work with in some situations. Plus, they hide the manipulation of object addresses, so programmers don't have to hassle with pointers. In C++, pointers work exactly as they do in C. In addition, pointers to structs and classes are intuitive. You dereference a function member just like you dereference a data member. For instance, if we have an elevator pointer which is initialized to an elevator object, we can dereference the member functions using the member selection arrow. An important use of pointers is as function arguments. This allows us to pass object addresses to functions. There are two reasons to pass addresses of objects instead of copies of the entire object. If you want the function to modify the outside object, and you create a local copy of the object, you will only be modifying the local copy and the outside object will be unchanged. The second reason for passing the address of an object is for efficiency. If you are passing a large object to a function, it may incur significant overhead to make a local copy of that object. If you don't need to change the object, you can pass a pointer to the object, which may be faster than making a local copy. To pass the address of an object to a function, the function must take a pointer to that type of object in its argument list. When calling the function, the user must either take the address of an object or pass a pointer. C++ has an additional way to pass addresses to functions. Some programming languages allow pass by reference, and this is included in C++. To declare a function argument as a reference instead of a pointer, you use the ampersand instead of the star, like this. This tells the compiler that it should expect an object, not the address of an object, as an argument, and that the compiler should take the address of the object. This means that you appear to pass an object by value, but the compiler actually only passes the address. This is the meaning of pass by reference. When you call the function, you must hand it an object like this. In the second call, the pointer must be dereferenced to produce the right argument type, an object. Inside the function definition, you treat a reference just like an object. That is, you use dots instead of arrows to select members. Here's what it looks like. Even though the compiler is actually using an address, it performs the dereferencing for you so you can treat the arguments as objects. This can be easier to read, and it has a second benefit. If you are trying to optimize a function's performance, you can easily switch back and forth between passing an address and passing a variable. All you need to do is remove the ampersand and you pass by value. Notice that you don't need to change any of the code in the body, since it already treats the argument as an object. By adding or removing the ampersand, you can use the Turbo Profiler to see which method improves the program's performance. It's also possible to return a reference from a function, which means the result of a function call can be used as an L value, that is, on the left-hand side of an equal sign. This can provide a convenient syntax in some situations, particularly for classes. Here, the reference allows you to directly assign to the private data member, which in effect disables the privateness. You're probably telling yourself, if a reference is just another way to manipulate an object via its address, why couldn't they leave well enough alone? Why aren't pointers good enough? Why do I have to make my brain cramp up learning how to use references? Well, those are good questions. First off, references weren't added just because pointers can be a bit tricky. They can make code much more readable. And there are certain instances in C++ where references are essential. That's it for this lesson. In lesson 11, we'll talk about static class members.